Okay, so now I want to move through the second. I'm now in chapter 2 of the book, which was sort of on mathematical preliminaries. And I just want to go through a bunch of things that theoretically everybody should know. But I do want to review it if you know it. And even, and there's some things that again, in data science more than most subjects, and it's true, by the way, in most subjects, I think doing the elementary stuff right is more important than doing the complicated stuff at all, okay? And so I want to go through the basic mathematical preliminaries I'm kind of going to assume people have. And, we'll talk about it, okay? So what does that mean? The first thing that I want to review is probability theory. Everybody has had some probability. Okay, I assume everybody here had some probability? You've never had any probability. How did you avoid it? What did you study when you were in
I was actually a humanities undergrad, so.
Okay, so learning a little bit of probability is a good thing, okay? So on some sense, what is important about probabilities that is both very, very simple and very, very hard is what is a probability? We know that there is, again, in the chapter I try to give this overview of probability theory. Definitely read that chapter. But the basic vision is we're trying to figure out for certain events how likely are they to happen. That's kind of what the theory of probability is about. And basically the probability of an event is a number that is basically between 0 and 1. And the important point is that every probability is between 0 and 1. And more to the point that if you sum over all possible outcomes, the probability is 1. Okay? So a coin can either come up heads or tails or lay on its side, right? There's three things that you could have. You could have a coin lay on its side. Probability of laying on, of coming up heads is 1/2 minus epsilon. Probability of tails is 1/2 minus epsilon. The probability of laying on its side is 2 epsilon, right? So the reason I make this much, I think, probability everyone should know. But the reason it matters is quite often in this course, people are going to be generating numbers that are between 0 and 1 and claiming they are probabilities, okay? And recognize that there is a difference. There's a second thing. It's not just, 0.432 is not a probability by itself. It is a number between 0 and 1. If, let's say, you're doing a classification problem, and you're going to be saying that, people are, that a living thing is a man, a woman, or a plant. Okay, these are the three possibilities. Often, you're going to want to say that for a particular person, you'll say, you'll have a classifier that will tell you what's the probability that it's a person, a man, what's the probability it's a woman, what's the probability of a plant. If you do this with three separate classifiers, like people might very well be, look at this object, is it a plant? What's the probability it is a plant? What's the probability it is a man? What is the probability it is a woman? Quite often these things don't, if they use independent classifiers to it, these things don't add up to 1. And so recognize that when you're talking principally about probabilities, they have to add up to 1. Any questions? That may seem kind of vague or says, that's obvious. Recognize when you're thinking about a classifier that's giving you what are the likelihoods of something happening in many different classes, you have to either normalize them explicitly so they add up to 1, or make sure that that's a consequence of your method. Any questions? That may still be too vague for now, but
In what context would that not
happen naturally? Suppose, let's say, that the example that I'm bringing to mind, because it happens all the time, is let's say you train a separate classifier. Let's say I'm going to be part of what we're going to be doing is building classifiers in here, right? And you could imagine a world where, I said the three classes were man, woman, and plant, right? You could imagine a problem where we take a look at a picture, okay, and we have to decide, is this a man, a woman, or a plant? okay? And again, I'm going to get myself in trouble here, but let's say there, and, here is, okay. So, you look at a picture, what is it? Is it a man or a woman or a plant, right? Okay, and I think everyone will agree. Let's just vote. What is that? Plant, woman, man, okay? Now, suppose, let's say, typically these things are built by, you have a lot of examples of plants, right? And you have a lot of examples of women, okay, and smiling ones, and you have a lot of examples of men, okay? And you can imagine training a classifier on the male examples, as we will talk about. Can we look at a picture and give a probability of it being a man, right? You could say there's men and not men, okay? And let's say I take a look at a picture of this thing. Okay, whatever. Okay, let's put here. Let's give him a mustache, okay, and a beard, right? Okay. What is the probability that this guy is a man? If you give it a classifier that's translated into men versus not men, what might the classifier say? There is a 0.7 chance of this guy being a man, right? Now, suppose we also build a classifier that looks at the women and compares you train on the women and the non-women, and you try to discriminate. Can you tell a woman from a non-woman, right? And if I run on that classifier, this is the probability of being a man, that classifier might very well give me a number. What's the likelihood this is a woman? It might come back and say the woman probability is 0.2, right? Now, let's say we train on the plants, okay? And we train on all the plants against all the non-plants, okay? What might the probability be if you're doing the test? That thing, is it a plant? What number might come back from that classifier? Okay, you want it to be 0.1 if it's a real probability, but if all you've done is train a thing that is plants against non-plants, there's absolutely no reason to believe that that is going to be 0.1. Does everybody see that? It's going to come back here. What's the odds of this guy being a plant? Maybe he looks like a vegetable, if you ask me. Okay? There's no reason why it might not come back like this, right? And you see now I've got numbers. Each one of these classifiers gave you a number between 0 and 1. It did not give you a probability. Does everybody see that? Or not a probability in the sense that it gave you a probability in the distribution of plant versus not a plant, but not a probability distribution in the multi-class case that you want. Okay? This actually now should be clear what I was saying, right? It was not nonsense. Okay? So recognize that quite often people will do things that will generate numbers. They will be between zeros and ones, but interpreting it correctly as a probability, requires some thinking. Yes?
Instead of training multiple binary classifiers like here, we can train a single multi-class classifier.
So maybe you're saying we should do a multi-class. Bottom line is you see that there is, it is not clear that you get probability distributions you want magically from just training on things. We agree that we'll talk about whether you build how you build multi-class classifiers later. Okay, but this is the point that I kind of wanted to make. Any questions? Okay, good. Okay. Now, probability and statistics are linked to each other a lot. Okay, and what is the difference between probability and statistics? There are people who call themselves probabilists. Okay, they study probability theory. There are people who call themselves statisticians. They study statistics. I interpret the relationship as follows. In probability theory, okay, you're in some sense making statements about the probability, about future likelihood of future events, things you haven't done yet. Statisticians generally analyze past data, okay, and they're talking about the frequency of past events. Okay, so there's a little bit of a cultural difference there. But the bigger cultural difference is that probability is a theoretical branch of mathematics that is based on definitions. take a course in probability, you get a large number of definitions, and all you're going to do about the rest of the semester is reason about these definitions. Does the world have to work according to those definitions? No, they're just definitions, and you play with the definitions, and everything else is a consequence of that. Someone I know who studies quantum computing. Does anyone know anything about quantum computing? Okay, you do. Okay, I don't. Okay, but they say basically that when I tell them this quantum computing is weird, why do you bother with it? He says this is interesting because it's kind of a generalization of probability theory. And in some sense, he doesn't want to build quantum computers. He doesn't, but that quantum computers work on this this model of what things do, and he's perfectly happy. He's defined what a quantum computer is. It involves some interesting math, and he's going to spend the rest of his life reasoning about that math. Okay, he is culturally a probabilist, right? A statistician is someone living in a real world trying to make sense of data and observations. And so they use some similar tools, but they are culturally different kinds of things. Any questions? Okay? Fair enough. Okay. Now, one thing we're going to worry about in here a lot are what we will call compound events, where, again, when you look at the definitions, probability theory has to be formally defined, and I'm going to try not to do it, so I may get into trouble. Okay, but you could imagine that there is this event, that every people in this room are either male or people in the have a universe of people. Let's say that half of them are female and half of them are male. Okay, and let's say that in this universe, every person is either above the median in grades or below the median in grades. What is the probability? So what is the probability if I pick a student at random, okay, that it's female? That should be 1/2. What is the probability that if I pick a student at random, they're above the median? That should be 1/2. What is the probability that if I pick a student at random, that they are both female and above the median? The answer is it depends. It's not that it's 1/4. It depends upon it. If all the women in here are smarter than all the men, which may very well be true, okay, then the women then it is the case that the probability that a student is both female and above the median would be 1/2. Does everybody see it? It could be it's as low as 0, okay, if they were completely orthogonal, okay. Or it would be 1/2, okay, the probability that a student is both would be 1/4 if these were independent, okay? Does everybody kind of get that idea? So we say that two events, okay, somebody being a person we pluck at random is a particular person is a person we pluck at random is female, okay? And the probability of both of these things happening, the intersection of these events. If the probability of both of those things true is the product of the probabilities of each of the individual things, that is independent. Okay? Any question about that? So what is good about independent events? Okay? If you take a probability course and you reason about probability, independence is your friend. Okay? Because if probabilities are independent, you can compute the probability of complex connected joint events as just the product of the individual ones. So for computing things, we want things to be independent, right? So as a probabilist, you're rooting for independence. As a statistician data scientist, we are not rooting for independence. Why is it? Generally speaking, we want to be able to make a prediction about something based on data or observations that we have, right? If I was fortunate enough that all the women were the students, all the people who were going to be above the median were female, I could have then made a prediction the first time I had to pick people to be in my class. It would have been much easier to pick the right students then, right? Because I could observe who was female, right? And if I could use that to accurately predict who was a good student, that would be better, right? So do you see that in data science and modeling, we want there to be dependencies, okay, which is different if you grew up in a probability world. Okay, when I talk to a probabilist, I'm desperate to assume things are independent so I can do the calculations. Any questions? Okay, good. Now, in particular, when we talk about making predictions, we're going to be interested in basically conditional probability. The conditional probability, this thing reads, oh, I guess, right, I'm allowed to do this, right? The probability of A given B is how I read this. A bar B is the probability of A given B is what is the probability of event A given that I know that event B is true, okay? And this is defined as the probability of both A intersection B, both A and B being true, divided by the probability that B is true, okay? Any questions? Okay? So conditional probabilities, okay, are what we're generally interested. I'm interested in, given that I have observed something about a student, what can I predict about them, right? And so it's going to be, what's the probability the student has this feature, given that they have these features, okay? And conditional probabilities only get interesting when events are not independent. What is the probability of A given B if A and B are completely independent things? You can work it out. The probability of A intersection B is A times B if they're independent, right? The probability of A given B is just going to be the probability of A if B has nothing to do with it, right? Any questions about that? Okay? So we are going to be, at various points here, interested in conditional probability. Okay? Any questions about that? Okay, good. Now, there is a famous tool for working with conditional probabilities that I'm just going to review just for us to think about now. We're maybe not going to use it as much as maybe I'm making it sound in here. But basically, there's an important reason, and we're going to use it actually. So let's say there's an important tool called Bayes' theorem for reasoning about conditional probabilities. Okay? And what it says here is that the probability of A given B can be computed. It could have been, okay, let's go back. The probability of A given B is computed by the probability of both being true divided by the probability of this being true. But maybe we don't know what's the probability of both of those being true. A useful thing to sometimes be able to do is to say that the probability of B given A can be computed as the probability of A given B times the probability of B divided by the probability of A. Okay? Now this looks mysterious to me when I see it. Okay? How many people have seen Bayes' theorem before? Okay, everyone but you who didn't take a probability class, right? Okay? Now Bayes' theorem is in one sense easy to derive. If you take a probability class, there's not that many lines of algebra to do this. Okay? But it always looks mysterious to me. So let's just go through an example of this to make sure we understand it. And so the example I would like to say, let's say that we have four things that have the property they can either be red or blue or both, or potentially neither. Okay? These first three things are blue. These last two things are red. Does everybody see that? This thing is blue and red. Okay? So let's work this thing out. What is, just by looking at the picture, what is the probability of red given blue? Okay? Well, let's make it even simpler first. What is the probability that if I pick a block that it's going to be blue? Okay? 3/4. Does everybody see that? Okay, this thing is half blue. I mean, you're blue if you have any blue on you, right? So the probability of blue is what? 3/4. What is the probability of red? It's half. Okay, I guess it's really 4. To be honest, I guess it's 2/4, right? Which is half, right? What is, by looking at the picture, what is the probability of red given blue? Okay, let's think about this. This is one that, make sure you be able to work this out for a second. Okay? What is the probability that a block is red if it is blue? Okay, well, there are 3 blue blocks. One of them is red. Therefore, 1/3 is the right answer. Does everybody see this? I want everybody to agree with this. Or any questions? See why that's true. What is the probability that a block is blue given that it is red? There are 2 red blocks, okay, and of those red blocks, one of them is, this should be 1/2. Does everybody see that? So by looking at the example, we can work these out. Now let's work the same thing out by Bayes' theorem, just to convince ourselves that Bayes knew what he was talking about, right? What is the probability, and again, I'm going to probably need some help because I never remember Bayes' theorem. What is the probability of red given blue? Okay? That should be the probability of blue given red times what? Probability of red divided by probability of blue. Do we believe this? Okay. Let us now see if that is right. Probability of red given blue is 1/2. And the probability of red was 1/2. And the probability of blue is 3/4. And so what is it? We multiply top and bottom by 4. This is 1/3. And this is right. Does everybody see that? Okay. And again, we can do it the other way around if we, well, let's do it just for the sake of comfort. Okay. What is it going to be the other way? Now let's reverse the role of red and blue. Now what do we have? The probability of red given blue is 1/3. Next one is going to be probability of blue times 3/4 divided by probability of red is 1/2. What does this work out to? Is this right? Is this what I should be doing? If so, what is this? This should be 1/4 over 1/2, which should be, if I multiply top and bottom by 2, by 4, let's say to make it easy, this would be 1 over 2. Does everybody see that? Okay, good. So Bayes' theorem clearly holds. Any questions? Okay. Why are we going to care about Bayes' theorem? And a lot of people who study, people talk about this. One way of thinking about Bayes' theorem, by the way, is as a way to update your confidence of things in terms of more information. That's really what this, or conditional probabilities in general, right? It's saying that if I have the evidence of A, how does my opinion about this change? Okay? Originally, and that's kind of why we're going to be thinking about conditional probabilities in general. Okay? Any questions?
So you're saying it's a way of checking our calculations?
No, it's kind of like a way of updating what is my confidence that about something. Suppose, let's say I want to figure, I have a student who I sign up to my office, okay? I sign up, who wants to work for me for a PhD, let's say. I don't know, is this student good or bad? I don't know, okay? Now they walk in wearing an MIT sweatshirt, okay? Do I think now, does that evidence, how do I refine my opinion of that based on this additional evidence, right? They start spouting nonsense, it goes down, right? So you can kind of think of it as being, you have an opinion originally, which is, I guess, the probability of B. How do you update your opinion on the basis of new evidence A that comes along, right? That's what really a way to think about this is. Originally, let's say I know I know what probability of B is based on my initial observation. if I have these two, I get more evidence. What's the likelihood that anybody in the population has that property? How many people wear MIT sweatshirts, right? And then, what's the probability of an MIT sweatshirt on somebody that's smart? Okay, it's giving me a way to update my confidence of B based on new evidence. And that's kind of where Bayes' theorem comes out to be helpful. Any questions? The example is probably a dumb one, but any questions? Okay, so fair enough. One thing about probability theory, or that we're going to be talking about a lot in here, are random variables. And random variables are sort of, are numerical functions where there is each value has a probability coming in. So, let's say I give the exam. The exam that I give in this class, every person in here will be assigned a number between, not a probability, but a number between 1 and 100, which was their score on the final exam, right? We can view that as being a variable. They call it a random variable, a variable, okay? If I knew, let's say, that 20% of you were going to get a 90 or above, I guess, okay, take it back. I'm getting a little bit too casual here. What a random variable is, to be precise, is there's a numerical function, and here is my numerical function. Okay, in this case, it's going to be the total on 2 dice. If I roll 2 dice, each are from 1 to 6. If that's my event, when I roll 2 dice, there are 36 possible outcomes. If I'm interested in the sum of the value on the 2 dice, I get a number between 2 and 12. Okay? A random variable is the function here. The variable is the sum of the dice total. For every possible value, numerical value here, there is a probability that it achieved. If I roll the dice, what is the probability that I would get a 7? It turns out to be 6 out of 36 dice rolls will do it. There is a 1/6 probability that I will get a 7 out of that. So quite often we are interested in charts that look like this, things that look like this, functions that look like this, where there is a space of possible outcomes, and every possible outcome there is a probability of it. Okay? Any questions? A probability density function, or a PDF, is a mapping for every possible outcome. What is the probability of that outcome? Any questions? What is the sum of all these probabilities going to be? 1, because this is a real probability distribution. Is that right? So a PDF is a description of the whole probability space here in some sense. Okay? In statistical data, it looks a lot like a histogram. Okay? If I was thinking about that exam case where at the end of the year we look at you guys, okay, and we take a look at you. Here's the exam scores. It was from 0 to 100. Okay? How many students got each grade? Maybe there'll be, how many people got a 30? Maybe 3 of you got 30. Okay? Hopefully more of you got an 80. Okay? Something like this. Does everybody see that? So a histogram, a plot of data, is generally speaking, the x-axis is a range of possibilities, the y-axis is a frequency, an observed frequency. And in a PDF, it's a probability that we're taking it for. Any questions about that? Okay? So quite often we will represent observed data as histograms, and quite often we're going to be interpreting it as probability density functions. We're going to somehow use this think of it as defining a probability distribution and then reasoning about it that way. Any questions? Okay. Now, there is another way to, talk about random variables and PDFs is something called a cumulative distribution function. A cumulative distribution function is basically the running sum of the PDF, the probability distribution function. Okay? So this is saying basically the probability density function told you what's the probability that the value of the function was exactly equal to 170. The cumulative distribution function instead is going to ask what's the probability that the value was less than or equal to the CDF. Does everybody see that? Okay. So there are different properties of these things. Okay. One way to think about it is that, again, as we sum this thing up, there's kind of like an integral differential relationship between the PDF and the CDF. Which has more information in it, the probability density plot or the cumulative density plot? Okay? The answer is the same. Okay? This is an important point. Okay? This has exactly the same information as this does. How would you figure out what is the probability? What is let's say I give you the PDF. Can you compute the CDF? How do you compute the CDF? You compute the running sum, bop, 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 as you go along there, right? Now, suppose I give you the CDF. Can you compute the PDF? Differentiate, that sounds complicated. Another way to think about it is, I take the difference between two negative things, right? If I had, it was the dice roll. If I had this, if I had the CDF of, what's the probability of getting less than or equal to 7 on a dice roll, or something like that. The probability of getting less than or equal to 7 on a dice roll minus the probability of getting less than or equal to a 6 on a dice roll is going to be what? That is going to be the probability is exactly equal to 7. Does everybody see that? So the probability density function and the cumulative distribution function have exactly the same information. Okay, they look different. This thing is always monotonically increasing, right? But they have the same information. Sometimes we're going to represent things as PDFs, sometimes as CDFs. You must be able to tell in your head what you're looking at, and you must realize that they are fundamentally the same thing. Any questions? Okay? And sometimes it's going to matter for us in terms of making certain operations easier on one or on the other. Any questions? One thing that's about cumulative distributions, generally speaking, PDFs are easier for humans to read. They have the same information. But PDFs generally, I think, are easier for people to read. Okay? And as an example here, this shows Tim Cook confidently standing, I guess, announcing iPhone sales. What does it look like iPhone sales have done this week, lately? It looks to me like they're exploding. That's what he's trying to show you, right? But that's because in a cumulative distribution plot, everything is exploding, right? Okay? Now, when you take the, instead, you took the derivative every quarter, how many iPhone sales there were at this point. You'll notice that it actually is quite flat, okay? In fact, it had gone down the last 3 quarters when he was bragging, okay? This is a tribute to the fact that, although they have the same information, it's easier to see global trends on a PDF, okay, than it would be on a CDF, okay? Any questions about that? Yes?
Why would we use a cumulative function if it is not, we are not able to intuitively tell that something...
Okay, so there are reasons why would you ever think, why am I bothering to tell you about cumulative functions, okay? Well, one reason, okay, again, there are, first of all, recognize you sometimes see them, and sometimes it makes sense to think of them in terms of this increasing thing. So, let's just think about why that would be. Well, one reason is that sometimes you like to see curves that are monotonically increasing, which this one is. One example of that tends to be when you're So certain things, okay, so let me give you two cases when there's cumulative-like things that we're going to do in this class, okay, cumulative distribution-like things. One thing has to do with when we talk about assessing classifiers. There's such a thing called a ROC curve, okay? Some of you may or may not have heard of it, where you're going to be looking at how many things did you get right so far, okay? Let's say that I want to predict. Okay, again, maybe I'm jumping ahead here. No, I don't want to ask you. I want to work this out for a second. The one example again. Okay, so let's say that I am making let's say I have a classifier here, which is trying to decide whether one of you is smart or not. Okay? You could imagine that over here is time. One by one, I'm going to have you people come in, and I'm going to make a guess, make a prediction as to whether you're smart or not, and I'm going to learn I'm right or wrong. Okay? One way to model this is over time, how many did I get right? Right? You could imagine a world where at the beginning, so let's say I had a classifier that was a certain 60% right. You would expect that overall, if I did this, on average, 60%, okay, one by one you people are coming in. I'm trying to guess, are you smart? Okay, and I'm going to learn whether I'm right or not, right? If I have a plot which shows over time what was my, how many I got right, okay, what properties would this plot have? The more we played, the number of people I've gotten right is never going to go down. Is that right? Okay. So like the cumulative thing, it will always go up, right? If I am right 60% of the time, we would expect pretty much a straight line that such that, at 60% of the total is where I would end up, right? But suppose to reach that, I started learning along the way, meaning I got better at this task. Let's say I ended up scoring 60%, but I learned as I was doing it. What would this plot look like? Okay? Suppose I ended up learning and got better at this task as time went by. Not exponential. It would probably look something like this. Does everybody see that? You say exponential, that may be what you mean, right? Suppose I started I started always getting it, right, and then I sort of got really dumb. You could imagine different shapes of these things. For certain distributions, it's easier to look at as a cumulative thing. Okay? That's, I guess, one reason I'll say for talking about it. I'll also talk more specifically when we talk about random sampling. There's certain things that are random sampling algorithms that are a lot easier when we talk about it in terms of the cumulative distribution than the PDF. Okay? So maybe that's more of an explanation than I wanted to give. Any questions? Okay, yeah.
So a PDF versus a CDF is basically growth versus rate of growth in a nutshell?
Not growth versus rate of growth. It is sort of, in one case, it is the again, we've moved a little bit away from the probability density function, but let's go back to this example here. In this case, this is showing what, if we were looking at a probabilities, where these were, what's the likely probabilities of individual events versus the probability, it's the probability of the exact value, the probability of this exact event happening versus the probability of all the events this or below happening. That is what I think the real difference here is. Okay? Any questions? Okay? And again, it's a little tricky to, again, one conflates PDFs with, probability distributions with histograms and things like that. But bottom line, the important thing to know is that these two things both represent random variables, and they both have the same information, and they are different things. So when you are reading one, you should know what you're reading. Any questions? Those are the most important things to take away. Any questions? Okay, good. Okay. So that is probability. Okay, we're finished talking about probability for now. Any questions? Okay, let's now talk about statistics. Okay, and the zeroth order statistics that you learned in high school or college or something like that, you probably learned about descriptive statistics. How do you take a bunch of measurements and compute, some properties of these measurements? And there are two very basic measurements that we're going to be interested in, which are basically, they call central tendency measurements, things like give me one number to describe the data set. What are the values really centered around? And there's another, which is a variational measurement, which is going to measure how much spread is there on these measurements. Okay? So if you're given a set of numbers, usually the simplest thing to compute is something like a mean, which is a centrality measure, and a standard deviation, which is some kind of a measure of spread. We're going to be interested in both these things on many, many data sets. Okay, so we need to know what they are and what this means. Any questions? Okay. So what is everybody's favorite measure of centrality? It is just the average or the mean. You sum these things up, okay, and you divide by n. And that gives you something like an average or a central measure of what the numbers are saying. Now, means are good central measures, but they aren't necessarily as useful in things that have, for example, outliers. What happens when you have an outlier element? If we took the mean wealth of the people in this room and we add Bill Gates, okay, the mean suddenly grows, right? Now, if I want to describe the bulk of the people in this class, that doesn't help me very much. Does everybody see that? Okay, good. It's also less clear, by the way, that the mean is really meaningful when the distribution of things is not symmetric. Okay? We are kind of used to mentally thinking about variables that tend to be sort of normally bell-shaped curves, things like this. We're used to probability distributions looking like this. What is the average height in the room? Well, it's probably clear that the average height is probably the most popular single height. There's less frequently people are shorter and long and taller. This is what we're used to, right? Now, the mean of a distribution that looks like this, is less of a good description of it somehow. Okay? That should be clear, right? So we sort of assume that implicitly with means we're thinking things are symmetric when we look at, and it doesn't have outliers. And certain distributions that we will encounter in this class, like power laws. Has anyone ever heard of a power law? What? 80-20 laws, power law type distributions. We'll talk about them later on in the class. But these things, taking the average of the values you see, yields a meaningless concept. Okay? And so we got to keep that in mind. Any questions? Okay, good. What other centrality measures are there? Okay, if we want to find the central, a measure of centrality of a set of n items. The standard one that is good in a lot of cases is the median. The median is the one such that there are half people above, half the people are below. Bring Bill Gates into the room, the median doesn't change. Does everybody see that? Okay, and so that's why that's a good thing. There are all kinds of other centrality measures that people have devised. Some people may have heard of the geometric mean. The geometric mean is what you get by, instead of averaging, adding the numbers and dividing by n, the geometric mean is the product of the n numbers where you take the nth root of it. Okay? Does everybody see what I mean by geometric mean? What is the arithmetic mean of 10 and 10? What is the arithmetic mean? Well, that's 10 plus 10 divided by 2. You're right, it's 10, right? What is the geometric mean of 10 and 10? 10 and 10, it's 10 times 10, that's 100. Square root of 100 is 10. You're right, it is 10. Okay? But that's not true unless all the items are the same. Does everybody see that? And in certain cases, okay, the geometric mean makes sense as a centrality measure. Okay? Now, why might that be? Well, there are a lot of properties of the geometric mean that are kind of curious. One thing that's true is that the geometric mean is always less than or equal to the arithmetic mean. Okay? And it's very sensitive to very small values. Does everybody see what happens if I take the arithmetic mean, the mean of 10 and 0? What is the arithmetic mean of that? 5. What's the arithmetic mean? What is the geometric mean? 0. Okay? So 0 plays the role of infinity in some sense in messing up our calculation when we talk about geometric means. Okay? Now, why might you care about using geometric means? And to show you that sometimes it makes sense, let's say that we were talking about ratios of things. Okay? So let's say that we are interested in, I give you some kind of ratios. Let's say we're looking at people coming in and we're saying how much stronger they are than, well, let's just think about it. Often we have situations where can anybody think of a situation where we might want to average ratios? Let's just think about this.
Like a rating system, for example, if a company is rated, say, on 1 to 5 on, say, environmental sustainability and on 1 to 100 on financial sustainability, and I need an average rating for the entire company, but they're rated on different scales. That's when I can average this out using a geometric mean?
Okay, let's say don't know. Okay, that's not the point that I'm trying to make. What I'm trying to make is that what should the average of 1 over 2 be and 2 over 1 be? Let's think about it. If I give you the average of, let's say I want to see how much better or worse something is. Okay? Yeah? Well, no. Okay, let me step back and say this again more carefully. Sometimes, why might you want to average ratios? Okay? Sometimes I might say people come in, and let's say somebody comes in and they are twice as strong as Skiena. Okay? I do a test, we do a battle, inside you're twice as strong as me. And somebody else comes in and they're half as strong as Skiena. What is the average of these people? Okay? Are these people, want to compare these people to Skiena? On average, how do they compare to Skiena? Okay, if you have somebody who is twice as strong as me and someone who's half as strong as me, to me, okay, what should the average of these things be? Okay, on some conceptual level, it seems like that should be 1. How many people believe that? You don't have to believe it. But do people see that if you've got ratios of these things, if I have somebody who's twice as good as me and somebody who's half as good as me, on average they're as good as me. Does everybody agree with that? But if you do the arithmetic sum of these two, what do you get? You say they're going to be better than me, right? And that's because, why is that? This is actually an important point, okay? It's because that if somebody is going to be less smart than me, there isn't that much room for them to be less smart for me, right? They can at worst be 0, right? They can be half as smart as me, a third as smart as me. They can't get lower than 0. But for being smarter than me, you can be a zillion times smarter than me, a quadrillion times smarter than me. Does everybody see it? There's more than one room. When you take ratios, bad things happen. There's more room one way around than the other way. Does everybody see that? And so if you just average these things, you get nonsense. Does everybody see that? Okay? And I am sure people in this class are going to try at some point to average ratios in here. Recognize that this is not really a sensible thing to do. This is kind of what I'm trying to tell you. And if you do it, then darn it, you should use a geometric mean. What is the geometric mean of 1/2 and 2? 1/2 times 2 is 1. The square root of 1 is, yes, you're right, that's 1. Okay? Any questions about it? Okay? So there are reasons why these other means sometimes come out to be handy. And the one that the reason or the case that you've got to realize you've got to do something different is when you're dealing with ratios. Any questions about that? Okay. Those are the basic ideas of centrality measures, okay? And which is the best one? You know, generally speaking, if it's symmetric and there's, you know, not outliers, things like height and weight, the mean is a fine thing. If you have skewed distributions, power laws, things like that, a lot of outliers, median is a more sensible thing to deal with. Any questions? Okay, so we got to think about that. Okay. Actually, let me not talk about this. Maybe I'm running behind. That's not so exciting. Anyway. Okay. The other statistic that we're going to be caring about is a variational measure. So everybody understand that. We talked about variational measures. Okay. The classic one that people are used to is the variance or the standard deviation, right? Everybody, I think, except you, have seen this formula. Okay. This formula is to compute the standard deviation, or sigma, of a set of numbers. What is the standard deviation? We take the mean, we compare every element to the mean. Subtract the value from the mean. Okay? Either we're going to get by how much is it above the mean, or how much is it below the mean, right? When we square it, the sign magically goes away. Does everybody agree? Right? So this is basically the average, something like the average squared difference between the mean and the element, right? And the square root of it basically brings it back down to the scale of the difference rather than the squared difference. Does everybody see that? Okay. So what does the standard deviation do? It gives us a way to compute how dispersed the numbers are. From the mean, right? You could imagine a distribution where, a PDF, where everybody was nearly equal. Okay, hopefully in a class like this, everybody is very, very good. If I plotted over here how smart you are, and probability, hopefully it will look something like this, right? Hopefully on the smart side, and maybe you're all identical, right? Or there might be a spread, okay, right? Does everybody see that? In the case of the distribution I talked about here, remember there was one where this was 0, this was minus 1, 1. In this case, the average was 0, but there was a great deal of spread, okay? And that's what these kind of statistics, like standard deviation, are supposed to tell you about. Any questions? So the standard deviation is a good way to tell the difference between, you know, tight distributions and spread distributions. Yes?
Also very sensitive to outliers, right? Because like if Bill Gates were in here, the standard deviation would be extremely high.
Right. So if we wanted to tell the difference between a world where, I said on a slide there that Bill Gates adds 250 to the average wealth of every person in the United States, right? You could imagine that how do I, if I just give you the average wealth without a standard deviation, we don't know if that includes Bill Gates or not, right? If the standard deviation is large, that means that there's a small number of people with a lot of money in there, right? And so the standard deviation gives us a way to, you know, that the standard deviation, you say, is sensitive to the number of outliers. The way I think is it measures the number of outliers. When we're computing a standard deviation, we want to know how spread it is, okay? When we compute a central tendency, we want to know what the distribution looks like. Together, the mean and the standard deviation will tell us a lot about the distribution. That is the key motion here. Any questions? Yeah?
Try to use the median instead of mean to compute deviation and to understand deviation. Will that be a better measure?
So you're saying, what if when you're computing a different centrality measure where you take the median value and you subtract those things? That seems like that, you know, that seems like you certainly could compute that thing, and it would be a score, and it probably would be a measure of spread. To be honest, I've never heard of that statistic, okay? So there's certain properties of the standard deviation that are very important to us, okay? So there's a reason why this is better than that for certain cases. But, you know, it may be interesting to compute, okay? But I don't, you know, we're going to be interested in certain mathematical properties of the standard deviation as defined like this that would go away if we computed it your way, okay? Any questions? Okay. Now, when I see this standard deviation formula, the thing that if you've seen this before, you've always wondered in your heart of hearts, sometimes you see this divided by n, and sometimes you see it divided by n minus 1. How many people know what I'm talking about? And how many people have been bothered by this? Okay, hopefully everyone who's seen it. What is the reason? Okay? It turns out there's a difference between whether you're talking about the sample. When you divide by n, they call that the population standard deviation. And when you divide by n minus 1, they call that a sample standard deviation. Okay? And one way to think about it is, suppose we have an island, and we want to compute the average weight of people on the island. Okay? If we have one person living on the island, should the standard deviation be in weight among the people on that island? It makes sense to me that should be 0, right? Because there is, in fact, no variation in weight. Everybody on that island weighs the same. Is that right? Now, suppose we go to an island like Manhattan, and we want to sample these things. Suppose I only sample 1 point from it. What do I know about the variation of people in Manhattan on their weight? I know nothing. It's not that there's nothing to know. I know nothing. Does everybody see that? So for n equals 1, if you're doing a sample of size 1, you know nothing, right? So n minus 1 is the right thing. If there really is only one thing there to know, then n is the right thing. Does everybody get that idea? I find that convincing. I'm not a statistician, but I find that convincing. Okay? But more to the point, you don't need to find that convincing. Any questions about that? I see people thinking about it. Okay? Do people get this idea? That if there is really only one thing there, there's no variation, and you would say it should be 0. Whereas if you sample something of size 1, you know nothing. Okay? And that's kind of what the difference between whether you divide by n or n minus 1 is. Okay? That said, usually we are going to deal with large values of n. In big data, ideally n is very, very big. And the difference between n and n minus 1 is bupkis. Okay, it doesn't matter, right? So basically, compute whichever one you want, okay? Or you think about it and then use whatever you want, okay? Because it isn't going to matter. Any questions about that? Okay, so that is variance. Okay? Now, what is important to know is that again, the distribution, once you know the mean and the standard deviation of a distribution, together you know a lot about the distribution, whereas with only one of these parameters you don't. Okay? This is an analogy. How many people have had like these inkjet printers, and suddenly one day a light bulb goes on and they say the cartridge is empty, right? Now, do you think that, now you notice the previous page, was the previous page lighter, you know, when you print these things, did the previous page look bleached out like there wasn't enough ink? You say yes. I usually say no. I get the idea that when the light bulb goes on, the previous copy to me often looked good. Okay? I don't know how many people share my suspicions on this. Okay? But when you get these cartridges, sometimes the cartridge will say, I am now empty, you can't print anymore. Right? Okay? And if, in fact, it was really empty, you would expect the previous copy to be almost blank. Is that right? Now, I don't notice that on my printers. I have a suspicion that the cartridge has a counter in it. And the moment you have printed enough copies, suddenly the company wants you to throw it out, right? Okay? So if so, what would be, let's say we could imagine that printer cartridges are made by two different kinds of companies. Good company, which is, going to let you print until there's no more ink in it. And another one that's going to tell you, going to have a counter and stop you at the promised amount of pages. How many what does the distribution of the number of pages you get from a copier look like? Okay? In the case of the good company, depending upon whether you printed things that used a lot of ink or a little ink, the number of pages you get from a cartridge should average be centered around, let's say, 3,000. But if you insisted on printing a lot of black pages, it would have been less. And if you printed almost all white pages, it would be more, right? If you had the evil company that stuffed enough ink so that they know they could get the 300,000 pages and then made you throw it out, you would get this distribution. Does everybody see that? The means are the same. The standard deviations differ. Okay? And so the shape of the distribution is quite different. But once you give me, the interesting thing is that once you give me both the mean and the standard deviation, you tell me a lot about the shape of any distribution. Okay? So there is a theorem that, that is worth knowing that says that in any distribution, okay, that there are always going to be at least the fraction 1 minus 1 over k squared. Okay, let's write this down. I think it's 1 over 1 minus k squared. That they're always going to be, if you think about it, here is a distribution. Here is the mean. There's going to be, if we had a frequency distribution, it could look something like this, right? There is a mean and there is a standard deviation. It is always the case that 1 minus 1 over k squared of the points must lie within k standard deviations of the mean. Okay? Let's think what this means again. Let's say this and think about this a little bit more deeply. Okay? Suppose, let's say, we had a, let's say that we looked two standard deviations from the mean. So from minus 2 sigma to sigma. Okay? The claim is, according to this, 75%, okay, of all the points, all the items, must lie within 2 sigma of the mean for any distribution. Okay? This is a very powerful thing if you stop to think about it, right? If I know the average height of people in the unit world, and I know the standard deviation of height, this tells me that there's going to have to be a certain number of people within that height range. Does everybody see that? So this is a very interesting thing. This is a kind of tight bound that together the mean and the standard deviation will tell you a lot about what that distribution has to look like for any distribution. Okay? Now, what's a weird distribution? Okay? Suppose we looked at our distribution over here, where we had a mean of 0, minus 1, and minus 1, right? And we had half the items here, none of the items at 0, and half the items at 1. What would the mean of that distribution be? 0. What would the standard deviation of that distribution be? It turns out to be 1. How many points lie within 1 standard deviation of the mean? 0, really. That's how you count, but you could easily say 0. Does everybody see that? And so for k equals 1, you get absolutely no bound. Does everybody see that? There's no guarantee that points lie within 1 standard deviation of the mean, right? But once you get further out, there is a guarantee that a lot of the stuff has to lie not that far relative to the standard deviation. Okay? Any questions about it? Yeah.
You mean from 0 to 1, the points don't have to lie in there, right?
So you're gonna, if you had an example of a world where half the items had a cost of -1,
Right.
half the items cost 1, had a value of 1, the mean would be 0. Mu, the mean is 0. The standard deviation sigma happens to be 1 if you compute it. The interesting thing, as you'll notice, is none of the population exists basically within almost 1 of the we're talking now about the equality is a separate thing, but you see that up to almost 1 on this distribution, within 1 minus epsilon of the standard deviation, nobody is there. Right? And if you look at the guarantee, if we had k equals 1 as our sigma, 1 times the standard deviation, in this case, we get no guarantee, right? But once we get twice the distance of the standard deviation, 3 times the standard deviation, a lot of them, no matter what the distribution is, a lot of the mass has to be there. Okay? Any questions about that? So the mean and the standard deviation together tell us a lot about the distribution. Yes?
Can you explain the distribution for the copy? I did not get it.
Okay, so what is the case with the copier? Okay? What if in a copier situation, every 1 is 3,000, right? Okay, now this is a limiting case, really, but let's say that everything is essentially everything is 3,000. Once by mistake they made it 3,001, they miscounted, or something like that, okay? The mean would be 3,000, and the standard deviation would be extremely small, right? So sigma would be extremely small in this distribution. Here, the standard deviation is pretty large. It's probably about like this, right? The mean is still sigma, okay? Right? These distributions look quite different from each other. Does everybody see that? But one interesting property of it is if you look at how many points lie within 2 standard deviations of the thing, in both cases it's going to be a lot of them. The standard deviation is here, 2 sigma is here, 2 sigma on both sides is here. Does everybody agree that at least 75% of that distribution lies within 2 standard deviations, right? In here, the standard deviation is extremely small, right? But what lies within 2 standard deviations? In this case, almost all of it, or maybe even all of it, right? So the property is that once you know the mean and the standard deviation, you know a lot about what the shape of that distribution has to be by itself. Okay, that's what this property is showing you. Okay? Any questions about that? Okay? When we talk about normal distributions, we'll see there's an even tighter distribution law here. Okay? But the important thing to see is it's not just that we as computer scientists compute means and standard deviations so we can print them on a paper and say, see, we know this thing. It's a mean, it's standard deviation. It's that together they tell us a great deal about the distribution. Any questions?
Sir,
Yeah.
so when we say a sigma distance from the mean, does it mean like on both of the sides? Or
Yes. So again, think about what this said. It means that the points that lie within 1 standard deviation of the mean were from here to here. They were 1 standard deviation to the left and 1 standard deviation to the right.
2 sigma distance.
No, it covers an interval of size 2 sigma, but the distance of any point is within 1 sigma of the mean. Okay? Any questions about that? Okay? So that's why we're going to care about these standard deviation thingies. Any questions? Yes?
But sigma also varies, right? So sigma in itself is not like a measure. We need to like divide sigma by the mean, right? Like to get like how many times the mean it is actually. Like
Okay.
visualizing, we cannot just say that this sigma is good or not. Or
Okay, so there's a question of whether, so if I tell you you know, I was measuring something and the standard deviation was, you know, 732. Do you say good or bad? Okay? And the answer is you can't tell anything unless it's the context of it, right? If I tell you an airplane costs $100 million, does that mean it's expensive? Well, you know, I don't know, okay? Okay, there's nothing to put in. So what you're telling me is that to put a standard deviation in context, you need to know the mean, right? Just seeing the standard deviation alone tells you nothing, okay? But the theorem that I just talked about, or I talked about in here, is in terms of the absolute value of it's saying that this is telling you what fraction of the points are near the mean, okay? And, you know, it says that a lot of the points are going to be near to the mean in standard deviation terms. That's the way to read what this thing is. For any distribution, a lot of the points have to lie near the mean in terms of distance as measured in standard deviations. Okay? And, you know, does that answer your question? Okay, kind of, yes. Okay, any questions? Okay. I'd like to say a few other things about variance, though. This idea that numbers jump around and that a mean is not the only thing you worry about. Okay? One thing that when I think of variance, okay, this idea of points that, you know, that jump up and down and there's a distribution and all this kind of stuff, I think of variance as some kind of force in the universe, okay? That it's not just a number you measure as the square of sigma, okay? The fact that things vary and understanding that observed values vary is something that you really have to understand because it explains a lot of things that don't seem like they're things that, you know, are just a result of a formula, okay? So, for example, when you think about the stock market, okay, there's this issue of signal to noise in any kind of a time series signal, okay? And that if you have the median, the mean is in some sense the average, the representation of what's going on. The amount of jumpiness in it is the variance, right? And, you know, in general, people like to just compute the mean and forget it. Or they like to compute the variance, the standard deviation, and print it out. But they don't think what it means very much. Okay? Recognizing that numbers jump around in a lot of data contexts is an important thing to understand on an intuitive level. And I'd like to go through a couple of examples of this, where people make mistakes about things. You guys aren't yet rich enough to invest in the stock market. Hopefully someday you will, okay? But you have this idea that there are different investors. There's 1,000 people or 10,000 or 100,000 people who earn their money by telling people how to manage things in a stock market, right? And 1 year, if you were doing it, you might earn 12% in the stock market. You would earn 6%, you would earn 18%, you would earn 3%. The guy who won 18%, he would probably, on doing this, brag and advertise and say, look at me, I got 18% income, okay? I'm a smarter investor than these guys, right? And the question of whether or not different investors have different skills is an open question, okay? It is, when they do a lot of research on things, in general, the performance of investors is basically random, okay? You got 18% this year because you were lucky. The next year, if we did it again, if you're a normal investor, the people who did best 1 year usually don't do best the next year, okay? Investment skill is something that a lot of researchers believe is essentially something that doesn't exist, okay? And that, everybody's going to get a number each year. If you invest, you're going to get something you earn. The question of whether you're really better than doing something by chance, okay? A lot of the effect of what you see is just variance. A lot of, the difference in investment performer is in some sense a random thing, okay? And that, it's very, very easy to mistake that variance, that random signal, for meaning something when there isn't meaning there. If, in fact, the sufficient market hypothesis is true and there's no difference between these investors, then basically what we're used to seeing as differences really is just random noise, okay? And that's something that, that you have to understand. Yes? What about Warren Buffett, okay? And again, when people do these kind of studies, I've read these kind of studies, it seems to me that they often say, well, there's a small number of people who seemingly do much better. And the reason is probably, in my guess, is that they're playing a different game, okay? So you can imagine a world of investors who are thinking about what's actually going on, and people who actually know how to suck money from a company. So often a Warren Buffett buys whole companies